If you subscribe to the channel, you'll get lots of interesting videos like this one. And if you like the video, it'll really help us out. Please comment down below for any other interesting things. That also really helps us out as well. Hi, welcome to another edition of AC Theory. So we're going to start talking about these things called graphs. So what is a graph? So it's something that allows us to model a lot of things in the real world. So if we want to look at, say, all of the roads in a given city, or maybe the layout of cities within a country, or maybe all of your friends on social media, we want to be able to understand the relationships between multiple people. So graphs are a model to understand relationships. Don't we all want that, right? To understand relationships between objects of some kind, whether they be people or literal cities. It's some kind of relationship between them. So the way that we visualize this is we have a bunch of points right here. So I'm going to draw I'm just going to draw a random set of points right here, and I'm going to draw a line between pairs of points. And I'm not going to put every single line in here, so I'm going to put that one in, this one in, that one, maybe this one, this one. I could leave a vertex completely out, like the one on the bottom there. And so all of these lines are going to be between pairs. It's not going to be between multiple of these points. It's only going to be within two of them. Okay, so this thing right here, oops. So yeah, so this thing is a graph. This whole thing, this collection of points and lines between the pairs of points. So let's talk about some of the definitions, because that's what we got to understand definitions in order to understand algorithms and other things about graphs. So each of these right here, of these points, instead of calling them points, we're going to call them vertices. And each one of them is a vertex. You could also call them nodes, and I may use that term sometimes. Some people use vertex, some people use node. It doesn't really matter. So what are these lines called then? So another term for these are called edges. So the lines that connect up the vertices are the edges. Okay, down here at the bottom, where we have a vertex with nothing connected to it, this is called an isolated vertex. And yeah, so this is the graph right here. So it's a bunch of vertices and lines connecting them, and edges connecting them. We could think about a graph that has a vertex connected to itself. So this is something called a self loop. I want to make sure that this is, yeah, it's appearing on screen. Yeah, so that's something called a self loop. But sometimes we omit those in our model of a graph. And sometimes, actually, we have multiple lines between the same pair of vertices. Okay, so here are some definitions. So if we have if we have self loops, or we have multiple edges between some pair of vertices, what we give a name to that as being a multigraph. So a multigraph is when we either have a self loop or we have multiple lines, multiple edges connecting up pairs of points. And any graph that isn't a multigraph, so if neither of these is true, the graph we have is what is called simple. A simple graph is just one that doesn't have any self loops and doesn't have multiple edges connecting up. So the graph before I added these orange edges right here, so the graph in blue right here, that is a simple graph because there's no self loop, assuming I get rid of that one. And, oops, yeah, and there is only one line in between every pair of vertices. Fair enough. But sometimes we want to have an asymmetry in the graph in terms of the edges. So if we look at this vertex, for example, we could either come out this way on that edge, or we can come from this vertex going along that edge. Okay, so sometimes we may want to add something called a direction to the edges. Maybe I want to go that way only. So maybe I can take this edge going this way, but not going back the other way. And we can certainly want that. So we could have edges being a term that is called directed. And so we can only traverse them in one particular direction. We can't go back the other way. So, and then in this case, the graph is called, as you might expect, directed. A directed graph. By definition, in the original case, a graph without a direction, so otherwise, is undirected. Not the best name in the world, but it's undirected. There's no direction on the edges here. Okay, so let's actually look at a particular vertex right here. So it has, and so we're in an undirected case, although it doesn't actually really matter here very much. So let's call this vertex V right here. So then all of these nodes that it connects to right here, those are called the neighbors of V. Okay, so the neighbors are the people who live right next to you, right? So here, all of the vertices that are adjacent to this vertex V are called the neighbors of V. If we had some other vertex out here that was not directly in contact with V, it would not be a neighbor of V. Okay, so neighbor just means directly adjacent to the vertex. So let's talk about a whole graph. So let's just say I have some graph. I'm going to make it up. So yeah, so here's a graph. I'm just making it up. So there are several things. If I look at, say, this part right here, so I'm taking a subset of the edges right here. I'm not taking necessarily all of them, but I'm taking some of them. So this right here is what is called a subgraph. Okay, a subgraph is just equivalent to saying a subset of the edges. Okay, and that's all that we actually need to do. Okay, and it's a proper subgraph. So another term is proper subgraph if it's not equal to all edges. So if we don't select an edge like we did here, then it's a proper subgraph. Okay, but in this particular case right here, if we extract what this graph looks like, it kind of looks like this. It looks like a little triangle, right? So this right here is what is called a cycle. That was not the best C and Y. Let's make those look better. It's called a cycle. So a cycle is just starting at one vertex and you just keep traversing and then you end up back where you started. And that's what a cycle is. So so then what, in the case if we don't have a cycle, so a path is a sequence of vertices that doesn't repeat. Okay, so a path is a sequence of vertices that don't repeat. So for example, if I started from here, then I worked our way down to here, and then I worked up to here, and then over to here. I never repeated a vertex along that route. And a cycle is effectively a path, but the first and last vertices are the ones that repeat. There are none in the middle that repeat necessarily. But the first and the last one definitely repeat. Another term that we sometimes talk about is a walk, is a sequence of vertices, and that's it. A walk can repeat vertices along it. It's just that a path doesn't. We say that a vertex is reachable. Let's just call the vertex V, reachable from Z. So from vertex Z, can I reach the vertex V? If there is a path from Z to V. Okay, and in the directed case, we would call this we would use something called a directed path, meaning we have to follow the direction of the edges along the way. So it would be directed path in that case, and it's also reachable in that case. So another term is, suppose that there's nothing in the graph definition that says that every vertex must be able to reach another vertex. So we could have something that looks like this. So maybe I have a little triangle right here, and then a square, so 4 vertices, and then maybe a little two vertex thing. And I could say that this whole thing is the graph. So each of these individually right here, each of these are what are called components. Okay, so each of these are individual components. And the way that you define a component formally is the set of vertices that you can reach from any vertex within the component. It's a maximal set of vertices, meaning you can't visit any more, for which every pair is reachable. Every vertex is reachable from any other in the component. In the directed case, though, this is actually a little bit more complicated because reachable is has an asymmetry. If you can go one way, you might not necessarily go the other way. So there's an asymmetry with directed graphs. So what do we do in that case? So in the directed graphs case, we have 2 different definitions. We have a strongly connected components. You could actually drop the word connected. Some people use the word connected here, but components is the term that's used there, and strongly connected is there. So that means, so what does strongly mean? It means every vertex in the component can reach any other. Okay, so just the usual definition. Every vertex can reach every other. But there's a weaker version, which is sometimes useful, which is called weakly connected components. And what are those? That's when, if we assume that the graph, if we look at the graph right now and we eliminated all of the directions on the arrows, then we get a connected a component. So if the directions on the edges were deleted, the graph, or I should say is the component itself. So the component is connected. Okay, so if it was an undirected graph, we keep all the edges there, we just remove the direction. But it's just, if that's the case, then it is still connected. So like over here, if I had a graph that looks like this, then if I put the, oops, I didn't do this one. Let's say that way. So if I put the directions like this, then I can, this vertex can reach these two over here. This one can reach this one. But, so this one's reachable, but this one right here is not reachable from anyone else. So this would be a weakly connected component. But if I instead said I'm going to have edges that look like this, where the arrows, the directions actually kind of go around in a clockwise way, then this is strongly connected because every vertex can reach every other vertex. Okay, and it's also weakly connected. So every weakly connected component, every strongly connected component already is a weakly one, but not necessarily the other way around. So this is weakly because in the original one, it was all connected. But in this case, the directions screw that up for this vertex right here. Okay, so some more definitions. What if we have something that isn't a cycle? So a graph without cycles is a tree. Okay, so that's the term. So a tree kind of looks like this. This is just an example. Okay, so note here that there is no cycle. I could theoretically go from this vertex to this one and back, but I'm traversing the same edge. So that's in some sense not a cycle. A cycle has to have length at least 3 in order for this to work. Okay, so that's something called a tree. And something that's not used a lot, but we will eventually use, I think, at some point. A forest is a collection of trees. Which kind of makes sense, right? If we have a bunch of trees, we have a forest. Okay, so suppose that we have a run-of-the-mill ordinary graph right here. It could have cycles in it. Okay, so right here, I'm just gonna make it up like that. So suppose that I take a subgraph of this graph. So I'm going to take a particular subgraph. Let's say I'm going to put that one in, this one, this one, this one, this, and this. So notice that the purple edges don't create a cycle, so it's a tree. And also note that it's touching every single vertex of the original graph. So this is something called a spanning tree. So a spanning tree is a tree that happens to hit every single vertex of a graph. So it's a subgraph, meaning that you not necessarily will take every edge with you, but it touches every single vertex. Okay, and one thing that you can show here is if there are n nodes in the graph, the tree has n minus 1 edges. In fact, in any tree, if it has x nodes, it has x minus 1 edges, and put proofs of that down into the comments. But yeah, so that is a lot of definitions about graphs because the graphs are extremely important. We're going to be seeing them all over the place throughout the algorithms that we're doing here and some of really cool things that we're going to be talking about in the future. So hopefully that was interesting. Leave your thoughts about graphs down into the comments. As always, please like and subscribe to the channel. It really helps us out. And as always, I'll see you next time.